This is video lecture number 3 for nuclear chemistry. We're going to talk today, so open up to transmutation reactions in your note packet. Transmutation simply means change. We are going to convert one atom of an element into an atom of another element. One type of transmutation is called natural transmutation. Just like it says, it occurs naturally. For example, uranium-238 will decay by alpha, which we can recognize from this symbol. So the other reactant is going to have a top number of 234 and a bottom number of 90. We look up atomic number 90 in the periodic table, and we see it is thorium. So the important thing to notice about a natural transmutation is the radioactive particle, in this case an alpha particle, is to the right of the arrow. This is not a chemical reaction. Chemical reactions involve interactions with electrons. This is a nuclear reaction, and nuclear means or involves changes in the nucleus. So we're going to investigate the uranium-238 decay series. It started above with the decay of uranium-238. The thorium-234 that forms will now itself undergo decay. We can see its beta, and if we put in the missing numbers, the top number is 234, the bottom number is 91, because 91 and minus 1 make 90. We look up atomic number 91, and it is protactinium. So what I would like you to do, go ahead and pause the video and go ahead and work out the next 3 steps in the decay series. And it should look like what I have written here. There are 9 more natural transmutations that occur before a stable product, lead-206, forms, which is stable and non-radioactive. The second type of transmutation is artificial transmutation, or elements that can be transmuted that are naturally stable. So Ernest Rutherford, if you remember him, he found out that most of an atom is composed of empty space, discovered that if he bombarded nitrogen gas with alpha particles, the nitrogen would convert into oxygen-17 by giving off a hydrogen atom. So when we balance these equations, we still do the same thing. Both sides have to add up. This adds up to 18, so the top number is 17 on this side because we already have a 1. The bottom numbers add up to 9. So the bottom number, the atomic number, will be 8. We look up atomic number 8, and it is oxygen. We can tell an artificial transmutation because there will be a radioactive particle left of the arrow. So in natural transmutation, there's going to be a particle to the right of the arrow. In artificial transmutation, there's going to be a particle to the left of the arrow. So if we take aluminum and we bombard it with alpha particles, left of the arrow, so it's artificial, what will be the missing particle? And we see it's a neutron. The phosphorus-30 itself will then decay into silicon by giving off a positron. This would be natural transmutation because the the radioactive particle is to the right of the arrow. So now we have two types of reactions that we need to know: natural transmutation and artificial transmutation. The third type of nuclear reaction we have to know is fission. Fission is the splitting of a nuclei into smaller fragments. It releases enormous amounts of energy. In fact, a kilogram of U-235 during fission can release as much energy as 20,000 tons of dynamite. We recognize fission as a neutron hitting a large nucleus, an unstable nucleus, that then breaks it apart into fission fragments. But more importantly, we recognize more neutrons. So these neutrons will then go off and hit other fragments, and we end up with what is called a chain reaction. Neutron hits, makes fragments, and more neutrons. These neutrons hit radioactive particles, and we release more and more neutrons, which can hit more and more particles, which release more and more energy. A typical fission reaction looks like this. You have to be able to recognize that something heavy gets hit by a neutron. It forms fission fragments, and it can be a whole bunch of different fragments, but more neutrons. So this one neutron releases lots of neutrons, and that's what causes the chain reaction to happen. It also gives off a lot of energy. The energy is produced when a small amount of mass from each atom is converted to energy. All nuclear reactions convert a small amount of mass into energy. Uncontrolled is an atomic bomb. Controlled, we use it in nuclear reactors. The big problem with fission reactions, nuclear reactors, is the waste. Fission products from nuclear reactors are highly radioactive and remain radioactive for thousands, if not hundreds of thousands of years. So the energy we get from it today, is it worth the while of having something radioactive for another 100,000 years to try to decay? The solid waste and liquid waste are sealed in special containers and stored underground. At least that's the plan. Gaseous radioactive wastes are stored until they decay to safe levels, where they can be dispersed into the air. The last type of nuclear reaction is fusion. Where fission is splitting, fusion is combining. We're fusing together. We're combining two light nuclei to make a heavier nucleus. We can't use large nuclei because the too many protons will repel a neighboring nucleus to such a degree that we can't bring them together. Fuels of fusion are isotopes of hydrogen, specifically deuterium and tritium. You have to recognize a fusion reaction where two light nuclei are fused together to make a heavier nucleus. Maybe something else might come off, and lots of energy. Fusion is a great reaction. Why? It produces lots of energy. The material is abundant. because we can get a supply of deuterium out of water. The products are non-radioactive, which is huge. But we have problems with fusion. It's very difficult to attempt to bring two nuclei together because they are both positively charged. So the hydrogen needs to have enough sufficient kinetic energy to overcome these forces of repulsion. Therefore, in order to occur, the reaction needs very high temperatures. Remember, temperature is kinetic energy. So enough energy to cause the particles to come together, and very high pressure to also try and squeeze these particles together. Currently, our issue is no container on Earth can hold a fusion reaction. Bear in mind that a fusion occurs in the sun. So you can imagine how difficult it is to get this process to occur. So we have four types of reactions we have to know: natural transmutation, artificial transmutation, fission, and fusion. That's it for today's notes. The fourth lecture tomorrow, very simple. So this is the main material has been given out. So you should be prepared to do the rest of the worksheets and to be ready for the test on Thursday. Have a great day.